Hi guys, this video is about another application of vector operations and a word problem. This is a problem dealing with resultant velocity. So we are given this information, and I just want you to know this is taken from the Larson Calculus with Early Transcendentals book at the 9th edition, and it was originally in section 11.1. So that's our citation, and then this is a summary of the information in the question. So we're told that there is an airplane traveling at 500 miles per hour with a bearing of 330 degrees. Now, until I read this in the book, I didn't know exactly what bearing meant. I knew that it gave you some sense of direction, but I didn't know what it meant in this context. In air navigation, bearing is a direction. It's measuring the direction clockwise in degrees from north. So if this is, well, let's say this is north, south, east, and west. If their angle, theta, and theta is given in degrees, that might be the bearing. So if we are going over here, and it's 30 degrees from north, that's a bearing of 30 degrees. Or a bearing of 180 degrees, well, that would be going this way. So when they tell us that the airplane has a bearing of 330 degrees, what they're saying is, if I draw this over here, the positive y-axis is true north. This is west, this is east, this negative y-axis is south. The bearing, just trying to find a marker that's darker color, being 330 degrees, that means we start up here, that's 0 degrees, and then we go 90, 180, 270, 360 would be all the way back here, but we only go to 330. So it looks like this. That's 330 degrees. And of course, that means that angle is 30 degrees. And so our airplane is on this vector. It's traveling with a velocity of 500 miles per hour at this bearing, so at that angle. Now we're also told that there is wind with a velocity of 70 miles per hour acting in the direction written this way. And I'm not exactly sure how you normally say that, but I would say that that's 45 degrees east of north. That's how we interpret this. So here is our north-south line. 45 degrees east of north is like right over here. So I'm going 45 degrees to the east of north. I'm on a line like this. And my velocity from the wind is 70 miles per hour. Now, obviously, this is not to scale. But if this is a 500 mile per hour velocity vector, now I'm adding to it a 70 mile per hour velocity vector that's pointing in this direction. Now, if I want to add those two vectors, I have to add tip to tail. So I'm going to do this vector plus this vector. Of course, my picture is not to scale. It's supposed to be the same length, and it's supposed to be parallel, and I don't think it's the same length or parallel, but that's the idea. Here's the wind velocity. And the question says, what is the plane's resultant speed and direction? Meaning, if it was going this way without any wind, and then this wind pushes the plane that way, well, then what happens? Where does the plane end up? I think we know, just from our studies of vector addition, it's this plus this. If I'm adding tip to tail, that's the one. That's the vector. That's my answer, that right there. But I don't want just this picture of the vector, which isn't that good because that's not very good and that's not to scale. I want the plane's resultant speed and direction. So in order to get the resultant speed and direction, I need to write the wind velocity as a vector. in component form, and then I want to write the velocity of the plane without the wind in component form. So I'm going to call this the velocity of the plane. I'm just going to call it v sub plane. Well, I know its magnitude is 500 miles per hour. Then I'm going to multiply by the cosine and sine of any of these angles, really, as long as you choose the appropriate one. If this is my vector, if this is 30 degrees, the angle with the horizontal here, if this is 30 plus this has to be 90, so this is going to be 60 degrees. And it looks like our wind velocity vector, not our wind velocity vector, our plane's velocity vector without the wind, it can be broken up into these two parts. One in the x direction, and that's next to the 60, so it's cosine of 60. But it's in the negative x direction, so it's negative. And then one in the y direction, it's opposite the 60. So I'm going to get that. And actually, with a little bit of right triangle trig, I can write down exactly what that is. Remember, whenever you're talking about a 30, 60, 90 triangle, this is not to scale. Let's say that one's 60 and that one's 30. The side lengths sort of go in the same order. They increase in the same order that the angles do. So the smallest angle is opposite the smallest side. So 30 degrees is opposite the 1. In a 30, 60, 90 triangle, the side lengths are 1, 2, and square root of 3. Opposite the 90, that's the longest one, it's 2, and the square root of 3 is in the middle. Square root of 3 is between square root of 1 and square root of 4. It's opposite the 60. So if I want cosine and sine of 60, which is what I need over here, I've got negative 500 cosine of 60 and positive 500 sine of 60. Now, according to my right triangle, cosine of 60 is adjacent over hypotenuse, so that's just 1/2. And sine of 60 is opposite over hypotenuse. That's square root of 3 over 2. So I got 1/2 of negative 500 is negative 250. That's 250 miles per hour in the negative x direction. And if I add to that 250 times the square root of 3 miles per hour in the y direction, add those two guys together, I get the original velocity of the plane before the wind came along. Now the wind, that can be represented by this vector here. I could use that vector there, but it's easier to see what's going on right here. So I'm going to say, well, that's 45, means that's 45. So the velocity of the wind is the magnitude, which is 70, times the cosine of 45, that's my x component, and then the sine of 45 is my y component. And hopefully you remember from right triangle trig, this is 45 and that's 45. This is a 45, 45, 90 triangle. The side ratios are 1, 1, square root of 2. So this is 1 over square root of 2, or if you remember from trig, we rationalized, we called that square root of 2 over 2. Can distribute your 70 through. So the resultant velocity is the velocity of the plane without the wind plus the wind velocity. And remember how we add component by component. I've got negative 250 and 250 square root of 3 plus 35 root 2 and of course 35 root 2. So it's a 45-degree angle. Add component by component, x's get added together, and y's get added together. Oops, 250 square root of 3 plus 35 square root of 2. Okay. Oops, sorry, it's off the screen. Now this is fine. That's the exact answer. But they asked for the resultant speed and direction. So I'm going to come up with this as a decimal approximation. You get negative 250 plus 35 root 2. It's approximately negative 200.5. And then over here I've got 250 root 3 plus 35 root 2. It's about 482.5 approximately. I asked for the resultant speed. That's the velocity, so I need to get the magnitude of that. I'm going to take my components, square them, add them, and take the square root. It's an approximation of my answer because these are approximate. I guess that's approximate too then. And I get about 522.5. All of these were measured in miles per hour, that was miles per hour. So this is a speed of 522.5 miles per hour. So we started with a speed of 500 going that way, and now we have, with the wind, adding a little bit of speed, we end up with 522.5 miles per hour. Now, in order to figure out what the bearing would be, I need to graph this in the xy plane. You can actually see it up there, but it'd be easier down here. Not to scale. I'm going negative 200.5 units in the x direction. I'm going positive 482 units in the y direction. So that's that. Now, that means that if I make a right triangle like this, this is 482.5 as a length, and this is 200.5 as a length, and we're calling it a negative x value because it's in the negative x direction. But with those two pieces together and right triangle trig, I can figure out what that angle is. I know that's theta. This is the side opposite theta, and this is the adjacent side to theta. So I can use tangent of theta. Tangent of theta is opposite over adjacent, because I've got those two pieces, and it's approximately 482.5 over 200.5. I'm going to use the positive one because I'm just interested in that angle there, and then I'm going to add to it to get the bearing. So theta is the inverse tangent of that. And I get, in degree mode, 67.43 degrees. Now that's that angle. The bearing is that angle plus 90, plus another 90, plus another 90. So it's that angle plus 270 degrees. So our bearing is 270 plus the 67.43, which is 337.43 degrees. So I've got a speed of 522.5 miles per hour at this bearing. So that is the third type of application problem you might see dealing with vectors. Now there are others that are possible. We've talked about three types. We've talked about problems in geometry, determining whether through points are collinear. We've looked at sum of forces problems and resultant velocities. But any problem that requires you to add or subtract vectors, multiply the vectors by constants, scalars, or find unit vectors in direction and use use the length and like a unit vector to find the vector in component form. All of that is relevant and possible as an application problem for the S4 section, which is about vectors and vector operations.